Thermochemistry. A great way to introduce the concept of thermochemistry and exactly what it talks about is to use a real-life example. For example, when you're super cold and you want to warm your hands, there's something called hand warmers. So chemical hand warmers actually involve a lot of what happens in thermochemistry. Warming your hands with chemical hand warmers involves many properties. Thermochemistry specifically is basically the study of chemistry and energy together. Defines the relationship, how energy involves in chemical reactions, how exactly that transfer happens, etc. When you have a chemical hand warmer and you open the package that contains the hand warmer, the contents are exposed to the air. So at first they're not, and then when you open it, whatever is inside that hand warmer, which is iron, is exposed to air, which is oxygen, and that then releases heat. And the release of heat is called exothermic. It is therefore warming up your hands. The useful product in that reaction, so if we look at that reaction here specifically, the iron and the oxygen making iron 3 oxide makes heat as well. And heat, not the iron 3 oxide, heat is that product that we are feeling. So when you have that hand warmer and you place it in, you open the package, you place it in your hand, the contents inside that package are released to oxygen, creating these two products. And the products that you're feeling is heat, where it being a product makes it an exothermic reaction, where exothermic means release of heat, releasing heat, and that's what you feel. So the product that we care about is heat. So the nature of energy. We've already slightly discussed what energy is in previous chapter, but just as a little review, energy is anything that has the capacity to do work. Very generic explanation of what we think of energy. Now, work also needs to be defined, and we've already slightly discussed that work is a force acting through a distance. So, real life example, imagine if you're moving and the box is too heavy and you push the box across the floor just to get it to that spot. Like if you're in the doorway and you need to just get it into the house, you're going to push the box, right? And you pushing the box is doing work. You're physically using work to push the box across a distance. The force of your hands and your muscles pushing that box over a distance is work. When you push a box across the floor, you have done work. And obviously there's so many more examples to just that concept. But for now, thinking of, all right, work is equal to force times distance. And that is one way that we look at energy. We also look at energy in the form of heat. Now, heat is the flow of energy caused by a temperature difference. So, for example, if you like to drink coffee in the morning before you go to class or work or etc., whatever you have going on in your day, you make your coffee and then you hold a coffee cup. And sometimes you hold it in your hand. The energy is transferred in the form of heat from the hot coffee to your cooler hand. So the cup with the hot coffee is hotter than your hand. And as you notice, after some time, usually the coffee is cooling down and your hand is actually warming up. And that's because that flow of energy, that heat, is being transferred from the coffee cup into your hand. So throughout this chapter in thermochemistry, we're looking at energy in total, where there's work done and then there's a flow of energy, which is the heat, due to temperature change, just like you have a hotter object and then a cooler object. The temperature changes causes that flow of heat in the form of energy. Now going a little bit back to something we've already talked about, other forms of energy, we've discussed kinetic energy, which is the energy of motion, and potential energy, which is stored energy. So putting this into an example, think of a pool table. And at the start of this pool table, you have a billiard ball rolling across, straight line, just going on its own, until it collides with a second ball that's actually staying still. So this first ball, as you can see here in this picture, is just rolling down, and then there's this second stationary ball and it collides with it right here. The rolling ball has energy due to its motion, that it is its kinetic energy. When it then collides here with another ball, it does work, resulting in the transfer of energy from one ball to another. The amount of energy it needed to move as it collides with the second object, that first ball then transferred its energy to the second as the second one then starts to move in the same amount of motion. The energy contained in the first rolling billiard ball is the kinetic energy, the energy associated with the motion of an object. Now, going a little bit back to that hot cup of coffee, that's not necessarily a solid substance. The energy contained in a hot cup of coffee we call thermal energy, the energy associated with the temperature of an object. Now, thermal energy is still a type of kinetic energy because it arises from the motions of atoms and molecules within a substance. So we know our big picture here is kinetic energy, the energy of motions. Even though when we're looking at thermal energy, we're looking at the energy that's defined because of the temperature of an object, like a hot cup of coffee. That energy has to do with the fact that that coffee is hot, but it's still kinetic because it has to do with how the atoms and molecules are moving around in that liquid substance. Then our other type of energy is potential energy. If you raise a billiard ball off the table, for example, you increase its potential energy. Potential energy has to do with the gravitational pull of a certain object. So if you're increasing and lifting it off of a table, that pull is going up, and the position is increasing of the object from gravity, and therefore the potential energy goes up. Now, another form of energy, a newer term, is chemical energy, which is the energy associated with the relative positions of electrons and nuclei in atoms and molecules, also a form of potential energy. Now, when we're thinking about different electrons, those are particles, and nuclei and atoms and molecules, before different reactions are happening, that's chemical energy as a form of potential energy because they're stored. Looking at this a little bit more visually, here's a little example of the difference between potential and kinetic. So gravitational potential energy, the pull of that object, when you're raising it up, it has a significant amount of potential energy. Then when you drop that ball, just like in the second picture, that potential energy is converted into kinetic energy. That amount, the magnitude of both of those energy does not change. It is transferred, just like in the example a little while ago where you had that first ball that had an amount of kinetic energy and it's rolling around in that table, and then it collides because there's this one ball there in the way, and it collides with that second ball, and that second ball then starts to move. It still has that same magnitude of energy if everything goes the way that you want. However, the kinetic here in this example and the example there, because it had original potential, the second ball, is transferred, which brings us up to the law of conservation of energy. The law of conservation of energy states that energy can neither be created nor destroyed. It is rather transferred from one object to another. Looking at a different example, if you raise a compressed spring, the potential energy becomes energy as the spring becomes kinetic energy, I should say, as the spring expands outward, because you just basically think you have a lot of stored energy, like when you're at the top of a mountain on a bicycle, and then you roll down. So all that energy that was stored is then converted, transferred into kinetic energy. It's a different type of energy, but it's the same magnitude. This brings us up to two new terms of when we're thinking of this energy flow, going from one substance to another, but defining it a little bit more of exactly what is being talked about. There's two terms, system and surrounding. A system is defined as the object of study. Iron reacting in hand warmers, for example, the coffee in a coffee cup, in which the energy changes. And the surroundings are everything else in the universe. So if we're thinking of the hand warmers as the example, where the iron inside is the system, your hand, your glove, the air in the glove, the air outside the glove, those are all the surroundings. According to the law of conservation of energy, the total energy change in the system and the surroundings must be zero. Since it's always transferred, nothing is lost or gained or created or destroyed, the sum of the energies has to be zero because it's constant. So therefore, we say and define that the energy of the universe must be zero. Therefore, it has to be the sum of the energy of the system and the surroundings. Now, we look at different units of energies, focusing on one mainly in this chapter, but there's a few other ways of looking at energy. For example, we can deduce the units of energy from the definition of kinetic energy, which is 1/2 times the mass and the velocity. Mass is in kilograms, and velocity is meters over second, but squared. Kilograms times meters squared over second squared is what 1 joule is equal to. So we say the main SI unit of energy is actually 1 joule, the amount of energy needed to move 1 kilogram of mass 1 meter of a distance. Another typical form of energy is a calorie, but lowercase calorie, which is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. For nutritional factors, a lot of the times you see calories with a capital C. Some of the conversion factors important for this chapter are that 1 calorie, lowercase, is equal to 4.184 joules. This is an exact measurement. This must be memorized. It comes up a lot, and it's really important. Now, the difference between the calories of this type of energy and heat and the calories on the nutritional factors that you see on different foods that you eat are by 1,000. So 1 calorie, uppercase, the ones that we see on nutritional labels, is 1,000 lowercase calories. And then when you're thinking about light bulbs, that energy, that's in kilowatts, and that conversion is 1 kilowatt is equal to 3.60 times 10 to the 6 joules. Just little review on some units of the energy. Now, another important energy is most of the time joules is given in kilojoules, so that conversion factor is really important. And it's just like any prefixes we've learned already, where 1,000 is a kilo. So 1,000 joules is 1 kilojoule. Now, going straight into deeper level of thermodynamics. So the first law of thermodynamics. Before I go into that, let's talk about exactly what thermodynamics is. It's just a very general study of energy and kind of its inner conversions, what's happening specifically in conversions and the transfer of energy from different types of systems and surroundings. The first law states that the law of conservation of energy. So basically the total energy of the universe is constant. The total amount of kinetic and potential energy, energy of motion and stored energy of a system that is in a system, we define as internal energy. So basically, thermodynamics is a general study of energy and its inner conversions. And the first law of thermodynamics is the law of energy conservation, which we've already learned. That energy is neither created nor destroyed, simply transferred, meaning the total energy of the universe is constant. It's always zero, where it has to equal the energy of the system plus the energy of the surroundings. Then we define that a little bit deeper. The total amount of kinetic and potential energy a system possesses is therefore defined as its internal energy. So we think of the first law of thermodynamics as internal energy. This internal energy is a state function, which means that it doesn't depend on however it took to get there. It depends on the final and initial states only. So internal energy is a state function, super important. The results depend only on the initial and final conditions, not the path the process used to get there. Now, going a little bit deeper into that concept, looking at a state function. So, if you think of climbing a mountain, and there's a couple different paths that you can take, where path A is 12 miles, path B here, if you look, going straight up this hill, is 5 miles. A state function is when you're only looking at the final and the initial states, where the top is the final, the bottom is the initial. Even if you took the initial from path A, which kind of gives you a longer zigzaggy version to get there. So this means that obviously path A has a lot more miles, so it's going to take a lot longer to get there, but it doesn't matter because eventually you had an initial and you had a final. So a state function depends only on its final and initial conditions. It doesn't matter if you took the longer way or the shorter way. It's not path dependent. So whenever you have a term, type of energy, heat, etc., that's state function, it's not path dependent. It only depends on its final and initial states, does not matter how it got there, what process it took to get there. So we look at the change in energy as the final energy minus its initial energy. And when we're talking about a reaction specifically, we think the energy of the products minus the energy of the reactants. Now, putting that in with what we just learned about system and surroundings and how it's a transfer of energy and the total energy has to be zero because it's constant, we look at this. So energy flow. When the energy of the system is negative and the energy of the surroundings is positive, the energy flows out of a system into the surroundings. So if the system is negative, it means that the energy from the system went into the surroundings. And now the opposite of that is true as well. When the change in energy of the system is positive and the change in energy of the surroundings is negative, that happens when the energy flows into the system. So it's negative when it goes out of the system, and it's positive when it goes into the system. But notice how they're always opposite sign because it's always being transferred from one to the other. Which brings us up to the sum of adding heat and work. We know we define as energy as the capacity to work and the heat flow through temperature change. Energy is exchanged between the system and surroundings through heat, defined as Q, and work, defined as lowercase w. So that interrelated with the internal energy, we define as the change in energy is equal to Q plus W, heat plus work. Now, heat is in the form of thermal energy, and it's positive when the system is gaining thermal energy, and negative when the system loses thermal energy. So, if you're getting warmer, you're gaining thermal energy, Q is positive. If you're releasing thermal energy, you're getting cooler, you are negative. Heat is negative. We already talked about work. Work that is done on the system is positive, and it's negative when it's done by the system. So in summary of that, the change in energy is positive as energy flows into the system. So when energy flows, into the system here, then this is positive. But if it goes the other direction, if energy flows out of the system, it's negative.